Temperature measurement of 9-phase induction motor drive without load and various load conditions. Abstract research and development, R&D, in recent days towards the power electronic system and motor drives concentrate their attention on multi-phase motor drive systems, due to some inherent advantages over three-phase motor drives like high torque density, efficiency, heavy loads etc. Since variable speed of AC power drives need converters for AC to DC power supply, the number of phases can be changed very easily. This led to increase the interest of multi-phase drive applications in the field of agriculture, aircraft, electronics vehicles etc. Almost all loads have nonlinear characteristics which exhibits heat at parts of the loads. When load is subjected to high current density cause equipment failure, hence presented work focus on the experimental analysis of temperature measurement at various body parts of 9-phase induction motor with no load and load condition using PWM drive. Data analysis has been done to monitor temperature effect on stator, rotor, and other parts of the motor by interfacing temperature module kit with laptop monitor screen using J-type thermocouples. Keywords: 9-phase induction motor, 9-phase inverter, PWM, microcontroller kit, temperature module kit, power analyzer. Introduction. Multi-phase motor drives gather more attention in recent years due to advantages over three-phase drives. Since variable speed of AC power drives need converters for AC to DC power supply, the number of phases can be changed very easily. This led to increase the interest of multi-phase drive applications. The advantages of multi-phase over three-phase motor drives are current and voltage harmonics, high torque density, cost reduction etc. Multi-phase drives have major applications in high-torque motor drives like agriculture, aircraft, hybrid electric vehicles, etc. Most of the failures in induction motors originates from the thermal reactions at various parts of the motor. This overheating at major parts like stator, rotor, bearing, shaft, and frame causes the failure due to thermal stress. Breakdown of stator winding insulation due to thermal stress is of the major cause of motor failure, hence, prevention of such failures is the major task. The thermal effect and losses on various parts of the motor can be reduced by implementing various modulating techniques. Inverters are the power converters which convert DC supply to AC output supply for desired phases. The topology of multi-phase inverters uses number of semiconductor devices, MOSFETs/IGBTs, with respect to number of phases. Switching singles are fed to switching devices, trough control generators. In PWM inverters, gate of semiconductor device is controlled by PWM control signals. The pulse width modulation, PWM, technique is implemented by switching of modulated pulses with constant amplitude and variable pulse width or duty cycle. PWM technique can be extended with switching signals of square, sinusoidal or sawtooth signals, depends on modulation technique. The presence of harmonics depends on selection of modulation index. Harmonics can be reduced by making modulation index to unity. Fig.1 shows the PWM control signal generated by microcontroller. The output load voltage and current can be changed by varying width of the pulses. Also, frequency of the two signals is nearly made equal 1:7. The presented work focused on the temperature measurement of 9-phase induction motor at various parts without and with various load. Generation of PWM control signals through the microcontroller 8051. Graphical analysis of experimental data monitored with power analyzer and temperature module kit. 2. Topology of 9-phase induction motor. Multi-phase motor drives constructed with n number of phases where stator windings are displaced by 360/n phase. As illustrated in Fig.2. The 9 stator windings, VASVIS, of an induction motor has displaced by 360/9, 40 degrees phase shift with each other fed by 9 legs and 18 switches of voltage source inverter, VSI, G1 G18. Rotor of the motor constructed with the squirrel cage winding to avoid internal locking between stator and rotor 8 to 11. 3. Modeling of 9-phase VSI. As shown in Fig.3. Modeling OD 9-phase inverter consists of 9 legs and 18 semiconductor switches, MOSFETs/IGBTs, connected in series to run 9-phase induction motor. 9-phase VSI is energized by DC power supply to control switches, VA6, to drive 9-phase induction motor, EA, EI. 9 legs are 360/9, 40 degree out of phase with other, and each leg has 2 switches conduct for the period of 180 degrees. All switches triggered by PWM signals 12 to 13. 4. Thermal model. Thermal modeling of the motor is developed according the principle of Kessler. According to the principle Kinder, the high of accuracy can be achieved by modest subdivision in geometrical parts of machine. Various body parts of motor can be identified as a node in the thermal network. The heat source, thermal capacitance and thermal resistance are associated as node with each other 14 to 15. The thermal model of 3 nodes, 3 resistance and capacitance are as shown in Fig. 5. The corresponding thermal network formed in between nodes capacitance and resistance. Fig. 5, thermal model of an induction motor, where P1, P2, P3 represents heat generation at stator, frame, and at body respectively. R1 is thermal resistance between stator and frame, RSF, R2 is thermal resistance between frame and body, RFB, and R3 is thermal resistance between body and ambient, RB. The equations for transient state thermal model of induction motor is as follows: 3, 4, 5. V. Methodology for the design of 9-phase induction motor. The methodology for the illustration of 9-phase induction motor is shows as a block diagram in Fig. 6. The AC power supply of 230 V converted to 12 V AC supply by using step-down auto transformer. Bridge rectifier converts AC to DC 12 V supply. 18 control signals are generated using controller IC, at 89S52, and fed to MOSFETs of 9-phase inverters through driver circuit. The generated control signals used to run 9-phase induction motor with no load and load condition. J-type thermocouples inserted to the various parts of the motor and connected to the temperature module kit. The module kit interface to personnel computer where the experimental data has been collected and used to draw the graphical analysis. The results are monitored with power analyzer to study various parameters of 9-phase induction motor. The complete experimental setup for the data analysis is as shown in Fig. 7. 6. Results and discussions. The temperature analysis 9-phase induction has been constructed experimentally and studied for a frequency of 10 Hz and 46 V. The harmonics and THD is obtained using power analyzer. Experimental results are monitored, studied, and compared with theoretical data. Fig. 8, A, B, shows the line to neutral voltage and current waveforms and various parameters, voltage, current, power, THD, respectively. The temperature of 9-phase induction motor at various part is as shown in the table 2. Fig. 9, A, B, and C, shows the experimental graphical representation of temperature data at various parts of the 9-phase induction motor with respect to time period of 4 HRS with no load and with load, 600 GM. 7. Conclusion. Data analysis of 9-phase induction motor with PWM voltage source inverter has been done experimentally for various loads. It is concluded from the experimental results that the rate of rise of temperature at various parts of 9-phase induction motor with various load is found to be increased with variation of load condition. The experimental work is to be extended to study the thermal model of 9-phase induction motor with various modulating techniques.